Okay, let's talk about integration by parts. So it's not actually a bad name, right? Once you know what it's talking about, the name makes a lot of sense. But let me start by saying that this is useful when your integrand involves a product of functions. So like x cosine x dx, or e to the x sine x dx, or so on. And when you have no idea what else to do, when your manipulations have failed, when you can't do a U substitution and your elementary integrals are not doing the trick, then you're going to want to do integration by parts. So, as I said, integration by parts deals with the product of functions. But we already know something about the product of functions, and that's the derivative of a product. The derivative with respect to x of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. This is not an integral thing. This is just your old friend, the product rule for derivatives. Now, why do I bring this up? Well, because integration and differentiation are opposites. And so you'd expect this to maybe tell us something useful about the integral of a product. And it does. So now if I go ahead and take the indefinite integral or antiderivative of both sides here, what do I get? Well, the derivative on the left-hand side goes away, right? That's an antiderivative. That's what it does. So this becomes f of x times g of x. And now the right-hand side comes under the integral sign dx. Now I'll go ahead and split the sum to the sum of the integrals. So I can write that. And then this is a little bit unmotivated, but what I can do very well is to just subtract this guy over, and then I can write f of x and g prime of x dx equals f of x g of x minus the integral of f prime of x and g of x dx. So in case it's not clear what I did there, I just subtracted this guy over. The left-hand side, and then I flipped the right-hand side and left-hand side, right? Nothing fancy. Okay, and so this right here is the essence of integration by parts. This is it, right? This is all it is. And we didn't do anything fancy so far. All we did is just write out the product rule, undo the product rule, and get this expression. So what's actually going on here is that we have a derivative of g prime of x on the left-hand side, but what integration by parts allows you to do is transfer that derivative to f. Right? So notice here, g doesn't have a derivative anymore. It's just g. Now the derivative has moved over to f. But you can't just do that without penalty. So you pick up this boundary term, f of x times g of x. Now, there's another notation for this that is helpful when we're actually doing the computations. And that's to set u equals f of x and v equals g of x. Then du dx equals f prime of x and dv dx equals g prime of x. And so du equals f prime of x dx and dv equals g prime of x dx. Right? As far as we're concerned, we can treat the differentials like fractions here. So What I've said about this so far has nothing to do with the integration by parts. This is just me introducing some new things and then taking some derivatives. But here's why it's useful. So where does f of x appear in this above expression? Right here and right here. Where does g of x appear? It appears right here and right here. Where does f prime of x dx appear? It appears here. Right, like there's a g of x in the middle, but it's still a product, and I can use the commutative property, obviously. And where does g prime of x dx appear? Well, it appears right there. So hey, look at that. I have everything I need to just rewrite this expression in a much shorter way. So this just becomes u dv equals integral of u dv equals u times v minus the integral of v du. And it kind of sucks that these letters are so similar looking, but this is just the way it is for some reason. Okay, so all I've done so far is write out the product rule, undo it, get this expression here, and then make some new definitions, rename some things, and basically condense my expression down in this new notation. And when we actually do these problems in practice, this is the form that we usually use. Now, what I've said so far applies to indefinite integrals, right? I don't have bounds on my integral so far, but obviously I can very well just add those in. So the integral from a to b f of x g prime of x dx is the product f of x g of x from a to b minus the integral from a to b of f prime of x g of x dx. It's the same thing, right? This is the same thing. I've just added bounds to make it a definite integral. And you might ask what this means here, right? Because this is sort of new notation. It just means that we're evaluating the product at the endpoints. So this is just f of b, g of b, minus f of a, g of a. Right, same way as we're evaluating the integral from a to b, we're also evaluating the product from a to b, but we need a different notation for it because it's not an integral itself. Okay. And then in the other notation with the u's and the v's, this is just a statement that ab u dv equals uv a to b minus the integral from a to b of v du. Okay. And so that's all the background here. This is just to be perfectly explicit for definite integral, right? So where we actually have some numbers and evaluation involved. Okay. So let's do some examples, right? Because this is all well and good in theory, but how does this actually work? Okay, so the classic example is to find this guy here. Now, why is this a candidate for integration by parts? Well, because I don't know off the top of my head what the antiderivative of this is. If you just asked me for this here, well, I could tell you it's x squared over 2 plus c. If you ask me for the integral of sine x, I could just tell you it's negative cosine x plus c. But who is the function whose derivative is x sine x? I don't know off the top of my head. And I'll be very careful here, right? Because this is not just the product of the individual integrals. The integral of a product is not the product of the integrals. If that were the case, then we wouldn't need integration by parts, right? And what is the integral of a product? Well, it's what we derived up here. So don't do this. This is very bad, and you can't do this. So, and why can't you do this? Because the derivative of a product is not just a product of the derivatives, right? You have to obey the product rule. And since integration of by parts comes from the product rule, you have to obey it here as well. Okay, so all that to say that we do actually need to use integration by parts here, which is obvious because otherwise I wouldn't use it in this video as an example. Okay, so how do I proceed? So like I said, um, in practice, we want to use this formula here, the one with the u's and the v's and all that. But then there's a bit of a game in identifying what u is supposed to be in v and so on. So one way to organize this, and the way I recommend, is just write out what you're doing in this format here. So I'm going to say u equals x. That's what I'm choosing. I'm going to say dv equals sine of x dx. Right, so then my integral is just u dv. I've just rewritten it with some new names. And what else do I need? I need du and I need dv. So du dx is just the derivative of x, which is 1. And that means that du just equals dx. I can cross multiply the differentials there. And then up here, well, I know what dv is. How do I get from dv to v? Well, I take the antiderivative. So this means that v is the integral of sine x, and that is negative cosine x. And I don't need to worry about the plus c here. Keep that in mind. I don't need to worry about that here. So let me just get rid of this. Oops. This middle guy here so that things look a little more organized. Okay, so there you go. I have everything I need to do this integral now, written out in this nice table format. So this is the way I would usually recommend to write it. U here, dv here, du here, and v here. Why should you write it this way? I mean, you can write it whatever way you want, but I think this way makes sense because the quantities that you start by assigning are u and dv. So you go to the original integral and you ask who's going to be u and who's going to be dv. So I said this guy is u and this guy is dv. And then from that, you can take a derivative to get du, and you can take an integral to get v. Right, so the guys on the bottom here are the sort of secondary or derived quantities. All right. So let's go ahead and solve this now. So the integral of x sine x dx is with the definitions I've made. It's the integral of u dv. But by integration by parts, that's just uv times the integral of v du. v du. Let's just plug these guys in. And I'll color code things here to be super clear. And because it's fun. Oh, shit. Okay, hold on, ignore that. I did the color coding. Oh, no, I didn't. What am I talking about here? So v du and du, let's make that. And then this actually might be doing more harm than good because I'm losing track of the colors. But okay. this is harder than it looks. Jesus Christ. Okay. Okay, so I have everything written out here. Okay, and so now we can actually do the integral. So the integral of u dv, sorry, it's the integral of x sine x dx, the definitions I've made. Now this is the integral of u dv. And by integration by parts, that's equal to u times v minus the integral of v du. And let me just color code things here to make it all nice and clear. So u will be orange, dv will be this guy, v, that's not a great color, v will be this guy, and du will be this guy. Okay, so this just becomes x times negative cosine x minus the integral of negative cosine x dx. Let me just move those negative signs around to make it a little easier. So this becomes negative x cosine x minus minus, so plus the integral of cosine x dx. And that's one of those integrals that, we know very well. That's our elementary integrals here. And the integral of x, or sorry, of cosine x is sine x c. And there you go. The integral of x sine dx is this. It's kind of neat. It's not a result that we've seen so far. And so we learned something new. Okay, so we can think of some other examples here. Let's go with, oh, I don't know. Let's say, the integral x e to the negative 2x dx. Right, this is another one of the prototypical type of questions here. I made it a little harder because I made it negative 2x, but this is a good one. So again, we're going to play the same game. Let's say u equals x, dv equals e to the negative 2x dx. And then so du dx equals 1, which means again that du equals dx. And now v is the integral, right, as before, of e to the negative 2x. And what's that? Well, it's e to the negative 2x, right, because e is its own integral. But by the chain rule, we have to make sure to divide by negative 2. Because when you differentiate this, a negative 2 hops down in front. So you want the negative 2 there to divide that, to kill it when it comes down. And remember, we don't care about the plus c when we're doing this part of the calculation. So v equals negative 1/2 e to the negative 2x, right? So it was e to the negative 2x over negative 2. I just rewrote that and brought the negative 1/2 outside. Okay, so I'm not going to color code it here because I don't want to do that again. So with the notation, this becomes the integral of u dv, and by integration by parts, that's u v minus integral of v du, which in this case is x times negative 1/2 e to the negative 2x minus the integral of negative 1/2 e to the negative 2x du, which is dx. And again, let's just put the negative signs in convenient places. So this becomes negative 1/2 x e to the negative 2x minus minus, so plus. Let me bring that 1/2 outside of the integral as well. E to the negative 2x dx. And again, we just solved the integral of e to the negative 2x. So that's plus 1/2 e to the negative 2x over 2 plus c. Don't forget the plus c here. And then so our final answer is just the following thing. So 1/2 times 1/2 is a fourth. Okay. So a question might come up, which is, how do I choose u? How do I choose dv? And the answer to that is that you want to choose a function. You want to choose the function becomes simpler when you differentiate it. What does that mean? Well, look up here. I could have chosen x to be my u, or I could have chosen e to the negative 2x to be my u. And then if I had done that, then x dx would have been my dv, right, the differential. But e to the negative 2x doesn't get any simpler when I differentiate it. It actually just becomes itself with another constant, right? So that really doesn't do much for me. It doesn't make my life easier. But x, well, that becomes super simple, right? When I differentiate it, it just becomes 1. And, same thing up here. And, your x won't, sorry, your u won't always be x, right? Sometimes you'll have an integral that just doesn't have uh, x times something. And in that case, what you can do is repeated integration by parts. So an example for you to try is to do like the integral of x squared e to the x dx. Now, x squared certainly becomes simpler when you take its derivative. So you want that to be u. So u equals x squared dv equals the rest of the stuff. And then du equals x, and then v equals e to the x. And when you proceed with this, you'll see that you come up against the integral of x times e to the x, and then you do another integration by parts. So sometimes, you just have to do it multiple times. But my point is that to choose u, just look for the function that becomes simpler when you differentiate it. That's it. Sometimes you'll have functions that don't become simpler. So the classic example there is e to the x cosine x dx when you take this integral. You say, okay, what do I do here? If I make this u, well, its derivative is just e to the x. It doesn't get any simpler. If I make this u, well, then its derivative is negative sine x, which is basically as complicated. And that'll happen sometimes. And this is a fun integral to work out. And you know what? Let's do it, actually. Yeah, let's do it. You know what? Let me just do the I'll do the integral of e to the x sine x dx. And then you do the other integral, which is almost exactly the same. I just think the signs here will probably be a little bit less of a hassle. So how do I choose my u here? Well, I'll just say fuck it and say u equals e to the x. It's not going to get any simpler, but whatever. And then v has to be the rest of the stuff, which is sine x dx. Then du dx is e to the x, which means that du equals e to the x dx. And sorry, this should be dv, not v. And then v is the integral of sine x, which is negative cosine x. So then v was negative cosine x. So I'll do my integration by parts. U dv equals uv minus v du equals e to the x times negative cosine x minus the integral negative cosine x du, which now is not the simple dx that it was before. Now it's e to the x times dx. All right, let's just be nice with the signs here. So negative e to the x cosine x minus minus is plus. So plus e to the x cosine x dx. So I'll just shuffle the product around a little bit. Okay, so that's kind of bullshit because you're trying to do this integral, and while you're doing it, you get another complicated integral, which we haven't seen before. So you say, okay, fine. I guess I have to deal with this somehow. And the way you deal with it is to just do another integration by parts. So let's come over here. And do the same thing. So here, let's say, and look, this is separate from the first one, right? So I'm taking this new integral that comes up, and I'm doing some separate integration by parts on it. You can think of this as part two of the problem. So here, so this is a different set of u's and v's. U equals e to the x. Again, why am I choosing that? Well, because I really don't have a choice, right? Let's just see how this works. And then dv has to be what's left over. That's cosine x dx. Then du, again, is e to the x dx. And v is the integral of cosine x, which is sine x. So now this integral here is, you don't have to write this out every time, but I'm just doing it to be clear. E to the x sine x minus the integral of v du, so sine x times e to the x dx, which I'll just rewrite as e to the x sine x dx, right? So I'm just moving that around. Okay, so now what we want to do is take this result and put it back up here. So we're going back to the original, the first integration by parts result that we obtained. So now that becomes negative e to the x cosine x plus this guy here, e to the x sine x minus e to the x sine x dx. And now you're saying, okay, this is nonsense, right? Like you asked me for an integral, and I just gave you another integral in exchange. Like, how does that work? Well, look at the magic here. So remember, the integral that we were evaluating in the first place is this guy here, right? Which equals this guy. So let's just write that explicitly, that the integral of e to the x sine x dx equals, after two integration by parts, it equals plus e to the x sine x minus e to the x sine x dx. But now here's where the magic happens. I have my guy on both sides. So I can just treat this as an algebraic quantity and I can add it over. Right? There's no reason I can't do this. This is totally legal. So I have 2 times the integral on the left-hand side. And that equals a totally legitimate algebraic expression on the right-hand side. So now how do I get the original integral I want? Well, I just divide by 2. And so there you have it, that the integral of e to the x sine x dx equals, let's factor out e to the x here. That'll be sine x minus cosine x. And I've been a little bit sloppy with the integration constant, but you need to throw that on at the end. Right, so I just divide both sides by 2, and I factor out 1/2 e to the x. And then I just rearrange the terms. So this is a nice result. Right, and so notice what I did was I used integration by parts twice, and then I saw that the expression I was looking for in the first place, the integral of e to the x sine x dx, it appeared in my final expression. And I just treated that as an algebraic thing, and I added it over to the other side, and I obtained a perfectly valid algebraic expression. Okay, so that's all that I have for now, and I hope this helped.